Our very last topic in this unit, I promise this is the last one, is rational and irrational numbers. So more generally, different sets of numbers. All right, we've already looked at a couple sets of numbers in the first unit. We looked at the counting numbers, at the whole numbers, and at the integers. And now that we've gotten some fractions and decimals involved, thrown into the mix, we've now also dealt with rational numbers. So we're going to start looking at irrational numbers also, and then classify different numbers according to what they are. So the first thing is this table, which gives us basically a set of what you might call perfect squares, right? So I have a number from 1 through 18, and then I have the square of that number. So 1 squared is 1, 2 squared is 4, 3 squared is 9, so on and so forth, right? All the way up to, so I have all these squares all the way up through 324, right, which is 18 squared. So again, those numbers are called perfect squares since they're squares of counting numbers. So that's the definition of what a perfect square is. It's a square of a counting number. All right. So what ends up happening is all of these counting numbers are square roots of their squares. So what is a square root? N is a square root of m if m equals n squared. Okay. And how do we represent a square root? We use what's called a radical sign, right? So that statement there, n is a square root of m, would be written n equals radical m, right? So let's give a couple of examples of this to see if we can show how this works here. So like 225 is the square of 15. So what that would mean is 15 is a square root of 225. Now why, or since, 225 equals 15 squared. So how could I write this with my radical notation? I could write 15 equals radical 225, right? So that's what it means for 15 to be a square root of 225, right? Because 15 squared is 225, and 15 equals radical 225. And you can do this with a bunch of other numbers also, right? So like what's another example? 9 is a square root of 81 since 81 equals 9 squared, right? So we could write 9 equals the square root of 81, right? 9 equals radical 81. So various statements could be created using all those different counting numbers and their perfect squares that we have above. Right. Now, one thing to remember that's important is the radical sign indicates that we're taking the positive square root of a number, right? But generally, though, positive numbers have two square roots, a positive and a negative square root. And the reason that works is because, let's say, for example, if I square negative 2, I get 4. If I square positive 2, I also get 4. So both 2 and negative 2 are square roots of 4. However, when you see the radical sign indicates that you're taking the positive square root. So for example, if I wrote the square root of 4, this means I want the positive square root, so I would get 2. If I wanted the negative square root, I would write negative square root of 4, right? So the negative square root of 4, that's going to be negative 2, right? But the thing to remember is that both 2 and negative 2 are square roots of 4, because both of them squared give you positive 4. But when you see this symbol, it means the positive, right? And then this means the negative square root. Okay, so just keep that in mind. And then the other thing to keep in mind also is, I don't mention this here, but when you have the square root of negative 4, this is actually going to be not a real number, because any number times itself will not give you a negative, right? If I multiply two positives, I get a positive. If I multiply two negatives, I get a positive. So nothing times itself would give you a negative. And I mean, you can see this on the calculator. If I use the radical sign on the calculator, square root of negative 4, I get an error message, right? Domain error, because the idea is it's not a real number. So you can't take the square root of a negative number for our purposes, because no number times itself gives you a negative. So when you're doing order of operation problems, what ends up happening is you treat radical signs like parentheses. So like if you had the square root of 64 plus 36, that's really like the square root of parentheses 64 plus 36, right? So you do the thing underneath that radical sign first. So 64 plus 36 would give you 100, and then this is actually going to be 10. But you should contrast that with if you had the square root of 64 plus the square root of 36, right? In this case, I have two individual square roots, so I would do the square roots first, then I would add at the end, right? So here I would do the square root of 64 and get 8, square root of 36 and get 6, and then I would do 8 plus 6 and I would get 14. So those two things are not the same, right? The square root of 64 plus 36 and the square root of 64 plus the square root of 36, right? Not the same. So just keep that in mind. And then, of course, what happens is not all square roots come out to nice numbers. Meaning, if I do the square root of 2 on the calculator, well, it's going to give me the square root of 2 because that's the only way to write the exact form. But what I can do is I can change my mode from what's called the math print mode to the classic mode. And now if I go in and do the square root of 2, look what's going to happen. It's going to give me 1.414213562, and it doesn't end. And did I see a pattern there? No, there was no pattern. So what happens here is I would just write this as like 1.414 dot dot dot, and I have no pattern. That goes on forever with no pattern. So the decimal part doesn't repeat and it doesn't terminate. So what we do is we call a number like the square root of 2 an irrational number because it doesn't repeat, it doesn't terminate. Another famous irrational number, of course, would be pi, right? Pi is an irrational number. The only way to write pi in its exact form is to write it with that symbol there, right? If I put pi on the calculator, where's pi on? Oh, here it is. It's not even a second. It's just a button. Pi 3.141592654. There's no repeating pattern and it never ends. So pi is approximately 3.14, but it's not equal to 3.14, right? It never repeats and it doesn't end, right? There's no repeating pattern and there's no end to it. So pi is another irrational number. So generally, the easiest way to form irrational numbers is just take square roots of numbers that aren't perfect squares, right? So like the square root of 3, that's irrational. Square root of 5, that's irrational. Square root of 6, that's irrational. Square root of 7, that's irrational. Square root of 8, that's irrational. But notice how I skipped the square root of 4 because the square root of 4 is 2. The square root of 9 is 3. So these are all irrational. But the square root of 4 equals 2. The square root of 9 equals 3. These are not irrational. Okay? So just keep that in mind. And then, of course, since irrational numbers were numbers whose decimal parts didn't repeat and didn't terminate, numbers whose decimal parts repeat or terminate are called rational numbers, right? So when you have most of them, I mean, pretty much all the numbers we've dealt with so far up to now have been rational, right? So like if I have 1/3, what is 1/3? It's 0.333 repeating. That repeats, so that's rational. If I have 1/2, that's 0.5. That terminates, so that's rational, right? If I have, we did 1/7 before, right? 1/7 is 0.14287 repeating. That's rational, right? So in this case, those were your repeating decimals, and this was your terminating decimal, right? So what ends up happening is a number is going to be rational if you can write it as a fraction with an integer in the numerator and denominator. Now, it's not always obvious that you can do that, right? But you can, right? So like any of these repeating decimals, you can. So like if you gave, let's do some weird repeating decimal like 0.1 0.15 repeating, right? What is 0.15 repeating? If I enter this in the calculator, remember we had said before that if I do this enough times, I want 1.5, 1.5, 1.5, 1.5, 1.5 a bunch of times until it recognizes that I want a repeating decimal, and then I turn it into a fraction, 5/33. So 0.15 repeating is 5/33. So I've written it as a fraction with an integer numerator and denominator, therefore it's rational. So that's another way to say that it's rational, right? If you can write it as a fraction with a numerator and denominator integer, right? And you can even do that with things that are fractions but aren't like that yet, right? So like if I had like 1.2 over 3, well, I'd say 1.2 over 7. That'd be nicer, right? That's not 1.2 is not an integer, but how can I turn 1.2 into an integer? What I can do in this case is I can rewrite this fraction by multiplying the top and the bottom by 10. And when I do that, I would get 12 over 70, right? And 12 over 70 then can reduce to, I mean, for our purposes, I've already showed that it's rational because I'm writing it as a fraction with integer numerator and denominator, but you can simplify this to 6 over 35, right? So 1.2 over 7 is also rational because you can write it as a fraction with the integer numerator and denominator. And then, of course, just the Venn diagram showing the relationship between numbers. So this whole big rectangle here is the set of, right? The whole big set is the set of real numbers. But the real numbers then can be broken up into rational and irrational, which are completely separate. But then inside rational numbers, you have integers. Inside integers, you have whole numbers. And inside whole numbers, you have the counting numbers. So based on this, a number cannot be both irrational and rational at the same time. A number that's an integer is also rational. A number that's whole is also an integer. And a counting number is also a whole number, right? Because of the whole idea about them being inside one another, right? Counting is inside whole is inside integer is inside rational. But those last three statements, the reverse is not true, like, right? So for example, an integer is also rational, but a rational doesn't have to be an integer, right? So like 1/2 is rational, but not an integer. So that's this one. So what about whole? A number that's whole is also an integer. So what's an integer that's not whole? Well, -2 is an integer, but not whole. And then, of course, the last one, a counting number is also a whole number. So what's a whole number that's not a counting number? There's only one of them, right? 0 is whole, but not a counting number. And that's the only example you can give there for a number that's whole but not a counting number, right? Because that was the only difference between the whole and the counting numbers. 0 was whole but not a counting number, right? For the integers that aren't whole, I could use any negative integer, -1, -2, -3, -4. And for rational that's not an integer, I can use any fraction, right? Whether positive or negative. But for the whole but not counting, the only one I can use is 0.